Okay class, I just wanted to do a quick video today in a couple of parts to help you with your truth table homework. So what I have on the board here are just some of the basic logical relations that we're going to have to think about, and just a very simple truth table. We're not trying to prove anything here, just look at all the different relationships between these letters. So I chose P and Q. It could be A and B, it could be X and Y, it could be any two letters that you want in the world to get started. This is when you have two letters and you're building a truth table. So we're going to start with our P and Q columns. You always start by giving two trues and two falses. And then in your second column, you alternate true, false, true, false. So if you have two letters, this is all you need. Every truth table is going to start just like this. True, true, false, false, true, false, true, false. And the reason that we do that is we want to get every possible combination of true and false. If P and Q are both true, you satisfy that right there. If they're both false, you satisfy that right there. If P is true and Q is false, we have that. If P is false and Q is true, you have that. That's every possibility. So that's how we always start. And then we can look at all the different relationships. So not P, we have our little tilde and then we have a P, is going to be the negation of whatever P is. So you just put in the opposite. So if P is true, true, false, false, not P is going to be false, false, true, true. P or Q, you know our V stands for or. In philosophy we have what's called an inclusive or. What that means is if either one of P or Q is true, then P or Q is true. Or if they're both true, then P or Q is true. So for P or Q, we have P and Q are both true. Well, that means that one of them is true. So either the cat or the dog did it. Well, if either one of them did it, then it's true that either the cat or the dog did it. And if the cat and the dog teamed up and did it, it's still true that either the cat or the dog did it. P or Q, if P is true, then P or Q is true. P is false, Q is true, that's still going to be true. And finally, where they're both false, P or Q is false because neither one of them is true. So the P or the Q is going to be false. P and Q is going to look a little bit different. If I say, look, today is Tuesday and it's raining outside, that statement, that compound statement is only true if both of the parts are true. So for any and statement, the whole thing is true only if both P and Q are true. If P is true and Q is false, that whole thing is false. If P is false and Q is true, that whole thing is false. And of course, if they're both false, that whole thing is false. Our third one, if P then Q, that's our horseshoe relationship. Where they're both true, that's true. Where P is true and Q is false, that's false. Where P is false and Q is true, that's true. And where they're both false, that's true. This one is the least intuitive of them all, but I can explain it with an example like this. If Obama gets elected, that's P, then he'll lower taxes. In this case, Obama got elected and he lowered taxes. So the compound statement, if Obama gets elected, then he'll lower taxes, turns out to be true. In our second case, if Obama gets elected is true, but he didn't lower taxes, so it's false that if Obama got elected, then he'll lower taxes. Our third case, if Obama gets elected, then he'll lower taxes. It's false that we elected Obama, but taxes went down because the other guy did it. Well, it's still true for logic purposes that if Obama had gotten elected, then we would lower taxes. Now that's one that sounds a little bit weird, but we have to give it true or false. And since we never elected Obama in this scenario, we can't really blame him for not lowering taxes. And the fact that taxes went down anyway is a good reason to consider it true. And finally, if neither of these things happen, if we elected Obama, then we lower taxes. Well, we didn't elect him and taxes didn't go down. It's still true, potentially, that if we had elected him, taxes would go down. So we call that true. And you just have to kind of remember that one. It's not the most intuitive one, but that's the way we're going to break it down in logic. Our last relationship is the P triple bar Q. That means logically equivalent. P is logically equivalent to Q when they have the exact same value here. So they're both true, so it's true that they have the exact same value. Here we have a true and a false. Here we have a false and a true. In both of those cases, they don't match up, so those are both going to be false. And finally, we have false and false. Those do match up, so the P triple bar Q is going to be true when both P and Q are false. All right, so that's our basic logical relationships for all of our basic connectors. The not, the or, the and, the if then, and the triple bar logically equivalent. We're going to pause there, and I'm going to come back after I set up the board again. Alright, so here's an exercise that's very similar to your assignment this week. You might have an argument that looks something like this. I just made this up. If the dog bites, then it is a menace, and the dog is a menace, so it doesn't bite. And that doesn't sound like a very good argument. We're going to prove that it's not a very good argument. So we have D, symbol is the letter for the dog bites. M is the letter for the dog is a menace. The next step is to put this into symbolic form. So if the dog bites, that's D. Horseshoe, then it is a menace. And the dog is a menace, so that's M. So it doesn't bite, and we have a negation there, not D. And we can label these P1, P2, and our conclusion. Okay, so we're going to take this argument and we're going to put it into a truth table to test for validity. And the idea here is you're going to build this digitally, so you're going to need a different row for each one of these symbols. So the D gets a row, the horseshoe gets a row, the M gets a row, even the knot gets its own row. So our letters are D and M, so that's always our first two rows. Then we have if D, then M, with D, horseshoe, M. They each get their own row. We have M once again, and then finally we have a knot and then a D. And on your piece of paper, it's going to look just like that, and we carry this across. So how do we always start one of these? We always start with true, true, false, false. And true, false, true, false. Different letters this time, but we're still always going to start our truth table like that. Now we have, alright, now our next step is to go right to the conclusion. So we're going to jump all the way to that last D, and that D is going to be just the same as this D. So that D is going to be true, true, false, false. Then we have the not D, so we need to just negate this row of D. So that becomes false, false, true, true. Now, I'm just going to cross this out. We don't have to worry about it. You can't cross it out on your computer. But the idea here, this is our main logical operator. Our conclusion is not D. And not D is best represented by this row of false, false, true, true. Now, to test for validity, what we have to think about is there any situation where all of the premises are true and the conclusion is false? That's the test for validity. So, theoretically, we only have to worry about these two rows. That's the only place where the conclusion is false. So that's the only place where all of the premises could be true and the conclusion is false. If you don't want to worry about that yet, you can keep filling out everything. What a lot of the examples in your book do, and a lot of the examples in the lecture do, is they just focus on the rows with a false conclusion. But I like to fill out the whole chart because I feel like it makes my life a little bit easier. So we have false, false, true, true. We can go to this premise, which is M. We're just going to carry our M over true, false, true, false. We have M here. I'm just recreating that M row everywhere I see an M. We have D, so I'm going to recreate D. And then the one where you have to do a little bit of work, if D, then M. Right? So that's our horseshoe relationship. So what we're going to compare is the D column and the M column. And we know for the if-then relationship, if true then true is true. If true then false is false. If false then true is true. And if false then false is true. So, we don't worry about this anymore. We don't worry about that anymore. And our test is there any situation where all of the premises are true and the conclusion is false? Well, here's our two premises, both true and a false conclusion. That right there is enough to tell me that this argument is invalid. We can keep testing if we wanted. We have both true premises and a true conclusion, that's fine. We have a false premise, so we're not worried about that row, and a false premise, so we're not worried about this row. To get an invalid argument, any row with all true premises and a false conclusion is enough to prove the whole thing invalid. If you don't have any row like that, then the argument is actually valid. Okay, we can pause there, and we have one more segment to go. The last thing I'm going to talk about today is the type of exercise you're going to do for your discussion. It's a little bit bigger, it's a little bit more complicated, but we do have a whole week and we're going to do it step by step. So I'm drawing from number 19 that says example, and I'm just going to show you what this would look like. So here we have our first premise, if not A, then B, that's our horseshoe, and C or A. And you'll notice that I put a separate column for every single one of these notations, except for the parentheses, which don't really do anything to the truth value. So you kind of keep that wherever they are. So that's our first premise. Our second premise is not B, and our conclusion is C and not A. So step one is to just set up your truth table. So the first thing you're going to do is set this up like this, and then you're going to put in your A, B, and C columns. All right. Now what's different than earlier in the videos, you're going to notice that we have 3 letters. That means our truth table is going to double in size. So it's going to be a big one here. We start with 4 truths and 4 falses. Then we do 2 truths, 2 falses all the way down. And then for your C column, you just alternate true, false. And what that does is the same thing it did before. It gets us if all 3 are true, it gets us if all 3 are false, and you have to take my word that it gets us every other possible combination in the middle there. Alright, so that's step 1. Once you finish step 1, you're good. Wait for me to clear it, and then when I do clear it, you're going to move on to step 2. Step 2 is going to be to evaluate your conclusion. So you want to get your conclusion, you want to figure out the truth value of your conclusion. And to do that, you have to figure out the main logical operator. And the main logical operator is the last one that you would fill in. It's the one that's most important since it's the last one you're going to fill in. So in this case, the C and not A. Well, the not modifies the A, so this column is more important than that one. And then you have to take the and is going to be the connection of the C and the not A. That makes and our primary logical operator. So to do this column, we need to bring the A over. So that's 4 truths and 4 falses. We need to negate the A. I know what you're thinking, it'd be a lot easier to skip that step. It would be easier, but we're going to do it just for completeness here. We're going to bring our C column over, the true, false, true, false, true, false. And finally, we're going to use this AND operator. And remember that AND is only true when both of the parts of the AND are true. We're not going to worry about this column, we're going to use the NOT because the NOT is the main operator for the A. The AND is the main operator for this compound statement. True and false is false. False and false is false. True and false is false. False and false is false. True and true is true. False and true is false. True and true is true. False and true is false. Alright, this is a rather unfortunate problem because remember, when is an argument valid? When is an argument invalid? When all true premises and a false conclusion. Well, we have lots of false conclusions here. So you have to do every row where you find a false conclusion. And your directions tell you to highlight this in green. So I'll just circle these in green for us. That's the rows that we have to worry about. That's step 2. Some of you have a conclusion that's really simple. It's just C, or it might be not C. If that's the case, then just do your conclusion. And then highlight all of your false rows. So that's the end of step 2. Step 3 says evaluate your premises. You'll work out the rows that were determined to have false conclusions. You will do this in multiple postings, usually 1 for each premise. So what's our closest premise here? Well, let's start with not B since it's right next door here. So we only have to figure out not B for the rows that have a false conclusion. So the first thing I'll do is bring over my B. So I have a false conclusion here, my B value is true. I'll do this in green for the heck of it. I have a false conclusion here, my B value is true. A false conclusion, my B value is false, and it's false. And it's true, and it's false. Those are the only rows that I have to worry about. Now I need to negate that, so that'll be false, false, true, true, false, true. Now, once again, I can limit my work a little bit. What makes an argument invalid? All true premises and a false conclusion. Well, I only need to worry about where I have a true premise. So now I only have to do 3 rows for my next argument. And that's good because my next argument is pretty big. So I'll switch colors again. Oh, sorry. Yeah, so step 3, we're still in step 3. I'm going to bring over my A for right here, which is a true. Bring over my A for right here, which is a true. I'm going to bring over my A, which is a false. I'm going to do my C, which is a true, false, false. And then I can do my OR, C or A, which we know the OR relationship is true when either part is true. So it's true here, and it is false here. Now, unfortunately, remember this whole thing is a premise, so just because I have a false doesn't mean I can give up on this one. I have to do this whole premise, and the main logical operator is right here. So we'll get to that soon. All right, so we'll bring over my B. Once again, we have false, false, false. We bring over my A, we have true, true, false. I can negate my A, that gives me false, false, true. I'm just going to cross these out, make a mental note. It's my not that I'm worried about. So if I have false, horseshoe, false, remember our horseshoe relationship? That's only false where the first part is true and the second part is false. So false and false is true. False and false is true. True and false is, that's our one false. Now, we're taking this column and this column, and we're using the AND relationship. True and true is true. True and true is true. False and, doesn't really matter, but false is false. What's our test? Is there any situation where all of the premises are true and the conclusion is false? Well, again, I can highlight right here and here. We have true premise. That's premise number 1. We have a true premise. That's premise number 2. We have a false conclusion. All true premises and a false conclusion. That's all as far as we have to go. That tells us that this argument is invalid. And that's how you do that. That 4th step is to call that invalid. Yeah. So, I know that's a lot, but this is written up in the directions. Make sure you download that step-by-step process. Watch this video, and hopefully you won't have too many questions. But if you do, send me an email. Thanks.